In this video, we're going to look at some applications to business and economics, focusing on savings accounts, some present value of annuities, as well as some other terms as well. So instead of having two videos for this section, a lecture and a practice video, since this is all kind of application problems, we're going to kind of combine this into one video. And then in 10.3, we're going to look at some other different kind of application problems. All right, so we're going to be focusing on finances in this video specifically. So first, let's think about a very generic kind of thing, and that is a bank account earns 5% interest compounded annually. If $100 is deposited into the account initially, we can find how much money will be in the account after any number of years, thinking about terms of a geometric series. We're going to think about in the next slide how to deal with geometric series as a total kind of thing. So let's think about just how these accounts work. That's going to help us for the rest of this video. So when we deposit $100, we're going to think about what happens to this money in year 0, year 1, year 2, and on and on and on. So in year 0, we initially have $100 that we deposit into the account. But after 1 year, we gain interest on that account. So we're going to add, so in year 1, we're going to have the $100 from before, plus we're going to add 5% of whatever's in the account at that time. Since that's 100, we're going to add 100 times 0.05. So in this case, that's going to be, if we factor out a 100 times 1 plus 0.05, or 100 times 1.05. That's how much money is in the account after year 1. In year 2, we're going to have that much money in the account, and we are going to add whatever is in the account times 0.05. Or another way of writing this is going to be 100 times 1.05 squared. If we do the algebra on that, I guess we can do that real quick. That's going to be, if we factor out a 100 times 1.05, we're left with a 1 plus 0.05, or 100 times 1.05, 1.05, 100, 1.05 squared. So we think about what happens in year 3. We're going to have 100 times 1.05 squared in the account, and we're going to add whatever that is times 0.05, and that's going to be 100 times 1.05 cubed. So what happens in year n is we are going to have 100 times 1.05 to the n. And note that what we've calculated here, each thing is going to be a term of a geometric series. Now in this question, we're not going to think about adding these things up, but we are going to think about that the answer to how much money will be in the account after year n is going to be this value. All right, so this kind of thought process, using the 1.05 instead of 0.05 because of the algebra, is how we're going to focus a lot with these problems. All right, so now let's think about geometric series, starting with the next thing here. An annuity is going to be a sequence of payments made at regular intervals, doing the same thing, a sequence of payments into an account, or whatever it's going to be at a regular time interval. So an example of that is an annuity pays $100 into an account each year, earning 5% interest compounded annually. So the difference between this problem and the previous problem is we don't just have an initial payment at the beginning, but we are going to keep on adding $100 into an account each year. And we can find out how much money is going to be in the account after a number of years, in this case using geometric series. So we're going to break this up into the different $100 that we input. So let's think about what happens with the $100, the initial $100. The initial $100 we know after year N is going to be worth 100 times 1.05 to the N. That's based on what we did in the previous problem because we know that any amount of money in the account is going to earn that much with this compound interest. So this is from the previous slide. Then we add $100 after year 1. So at the end of year N, this has been in the account for N minus 1 years because we inputted it not at the beginning, but a year after the beginning. So this $100 is only going to be worth 100 times 1.05 to the N minus 1. Then we think about what happens to the $100 that we input after year 2. We think about how much is that $100 worth in year N. Note that this is going to be just for N minus 2 years that it's in the account. We have 100 times 1.05 to the N minus 2. And note that we're going to keep on doing that forever until we have the $100 we have after year N. How much is that money worth after year N? Well, that's just worth $100 because it hasn't accrued that interest as the other ones does. So to recap what we're doing here, each year we're paying $100 into the account. We're going to track what happens to each of those $100 using the things we did in the previous slide. So the initial $100 gains the most interest. That's going to be 100 times 1.05 to the N. The next $100 earns the next most interest. We have to the N minus 1 down the line till we get to the last $100 actually gains no interest yet, and that's going to be worth just 100. So what we're going to do is we're going to add all of this together. This is all of the money total. So we're going to add these together. We can write this as 100 plus 100, 1.05 plus 100, 1.05 squared all the way to 100, 1.05 to the N. And that is a geometric series with R equal to 1.05, A equal to 100, and N equal to, or I should say that there are N plus 1 terms. So we could find the value here by using our formula, S sub N plus 1 maybe. It's going to be equal to A 1 minus R to the N plus 1 over 1 minus R. We're using N plus 1 here because we have N plus 1 terms. This is going to be 100, 1 minus 1.05 to the n plus 1 over 1 minus 1.05. That's how much money will be in the account after n years, and put in n value for n, we can get that value. All right, let's move on. So another thing we're going to think about is the present value of an annuity. And that's something different than what we had before, but it's how much money must be in the account to make a series of fixed payments for a fixed amount of time. So our example here is going to be, we have car payments that we're going to make every month for 36 months. $100 a month for 36 months. We want to find out how much money must be initially in the account if we have a monthly interest rate of 5% compounded monthly. We can think about this as the same idea as an annual rate of compounded annually, whereas we think about months as car payments are usually given in months. So what we're going to do here is define how much money do we need to have in the account to cover each car payment. So how much money must be in the account to cover each payment. And we're going to break it up into each payment. So our first payment is $100. And the money that we need in the account, since this happens now, we need $100 there. Since this is at the beginning, there is no interest involved here. What gets interesting when we think about the second payment. It's also $100, but now we don't need $100 because we can accrue interest on some other money. So we can think about, we're going to let P, standing for present value of the annuity, P is going to be equal to how much money we need. So if I have P, if I'm going to be in there for 1 month, that money's going to be in there for 1 month. If I multiply that by 1.05, that should be equal to 100. Again, this is saying that this is how much money this is going to accrue after 1 month. It earns the money P plus the money P times 0.05, like we did in the first slide. So this means that the money that I need here is going to be, if I multiply by 1.05 to the negative 1, it's going to be 100 times 1.05 to the negative 1, or 100 divided by 1.05. Then we think about, what about our third payment? How much money do we need there? Again, we're going to let P be the money that we need. But here, this money earns interest for 2 months. So that's 1.05 squared, and that has to equal 100. So here, the money that we need is going to be 100 over 1.05 squared. And we can do that all the way to the 36th payment. Here we're going to have P, but we're going to have 1.05 to, it's going to be in that account for 35 months, equal to 100. So P is going to be equal to 100 over 1.05 to the 35th power. So adding all this up, this is how much money we need total. So if we add all of this up, we have 100 plus 100 times 1 over 1.05 plus 100 times 1 over 1.05 squared, all the way to 100 1 over 1.05 to the 35th power. So how much money are we going to need? Well, we're going to need, this is a finite geometric series. We know the total here is going to be A 1 minus R, which is 1 over 1.05, to the n here is 36, divided by 1 minus 1.05. We can use the calculator to find that out, and we should know that this is going to be less than 36 times 100. Right? That's how much money we would need total if we didn't have this account gaining interest for us. But because we can have the account gain interest, we're going to have to spend less than that to cover the cost of the car. All right, a few more examples. Next one has to do with a multiplier effect. This is an effect that goes beyond the initial effect, and we're going to look at a tax rebate to kind of understand what's going on here. So we're going to say the government gives $1,000 as a tax rebate to 100,000 people. A tax rebate we can think about as a tax refund that happens immediately. It's not necessarily when you do your taxes. It's just given at a certain point. You can think about this is similar to the pandemic relief stipends in some way. It's just money that the government is giving to people for some reason or another. So what happens here is that the government gives $1,000 to 100,000 people, and these people are all going to save 40% of that rebate, and they're going to spend the rest. So when they spend the money, that becomes more money in other people's pockets that they spend. So when we're thinking about how much money is spent total, it's not going to be just that first round. And we'll kind of do a little diagram to understand this. So we have the government is going to give $1,000 to 100,000 people. And those people are going to save, we're going to say they're going to spend 60% of it. They're going to save 40 and they're going to spend 60%. So 1,000 times 0.6 is $600. They're all going to spend $600. So all these people are going to spend $600, which becomes more money in other people's pockets, in business owners' pockets or whatever it is, that money is spent. And those new people that have the money, even if it's previous people and it's kind of overlapped, it doesn't really make a difference, are going to take that $600 and they're going to spend 60% of it. We're assuming that all people, when they get money, are going to save 40% of it and they're going to spend 60% of it. So here we have $600 times 0.6 is going to be $360 they're going to spend out of that $600. So all these people are going to spend $360, which becomes money in other people's pockets. And it just keeps on continuing. That $360, people save 40% of it, they spend 60% of it, and this is going to give us $216, and again, this just repeats. So they all spend $216 and just goes and goes on forever. So the idea here is that the $1,000 to each of those people at the beginning, when we're thinking about how much money is going to be spent, it's not just what the first people spend, but it goes down and it kind of trickles through the economy and people get the money, one, two, three, four steps later that they can also spend. So if we think about how much money is being spent here, well, we have at the beginning that 100,000 people are going to spend $600, right? 60% of that $1,000. Then, past that, we're going to have that money times 0.06 is going to be spent. All that money was spent, and 60% of that, sorry, not times 0.06, times 0.6 is going to be spent total. Then all of that money is going to be spent, or 60% of that is going to be spent, and we just continue on forever until eventually, we just kind of run out of money there. So we think about how much money is being spent. This is a geometric series with A equal to $100,000 times 600. R here is 0.60. And since this is less than 1, we have our infinite geometric series. This is going to be 100,000 times 600 divided by 1 minus 0.60, or divided by 0.4, which would be equal to, which is $150 million being spent. And let's think about at the beginning, just to kind of see what we're talking about here. At the beginning, the government gave $1,000 to 100,000 people. So that is a total of 100 million. So with an initial investment of $100 million into the economy to people, that actually turns into 150 million being spent throughout the economy. And this is the multiplier effect that's actually happening. It's not that just 60% of that 100 million is going to be spent, but it actually goes beyond that. We can use a geometric series to help us with it. All right, I think we have one more problem here. This has to deal with market stabilization point. So the idea here is that a product, the market stabilization point of a product is going to be the total number of units in circulation in the long run. And the idea is that when you have a product in circulation, a certain percentage of those products are going to break because of whatever reasons, because of overtime or malfunction, whatever it's going to be. So it's not just going to be adding the same amount each year, because some is going to be decreased at some point. So here we have an example of the US Mint produces about 7.4 billion pennies a year, and about 5% of them are removed from circulation each year for whatever reason. They're lost, people save them in a piggy bank, whatever it's going to be, they're no longer in circulation. So we can think about how many pennies are going to be in circulation total. So similar to what we've done in previous examples, we're going to think about the pennies added this year. And that's going to be 7.4 billion pennies. And we're not going to say that any of them are going to fall out of circulation because they've just been added and not any of them are going to be lost. If we think about the pennies added last year, well, last year we added 7.4 billion pennies, and we also lost 5% of those pennies. So total, we have 1 minus 0.05, or 7.4 times 0.95. Is how many pennies we have from the previous year. If we think about the pennies added 2 years ago, well, we added 7.4, but then we lost 5% of them, right? And then we took this whole thing and we lost 5% of that. In total, we can think about this as the same idea we've had before, that this is going to be the 0.95 squared. That we've kept 95% of our pennies, but that had to be kind of 2 iterations over 2 years. If we think about this, what about the pennies that we added 15 years ago? Well, they're still in circulation, there's just less in circulation. There's going to be 7.4 billion, but we're going to have 0.95 to the 15 power. So the total amount of pennies is going to be adding up all of those together, and it's going to be 7.4 plus 7.4.95 plus 7.4.95 squared, and that's going to go on forever. All right, or we can think about if we went for the long run, that would be what happens. So this is going to be a geometric series, infinite geometric series with A equal to 7.4 billion, we should say billion here, and R equal to 0.95. So we have A over 1 minus R, 7.4 over 0.05, which is equal to 148 billion. So what happens at this point is once you have about 148 billion pennies, when you add 7.4 billion the next year, you are getting rid of 7.4 billion throughout the pennies from the previous years. So this is a stabilization point. Once you reach this 148 billion, now it's just like the number of pennies is going to stay at that amount, and it's not going to increase or decrease. In the next video, we're going to look at some applications due to natural sciences, but we're going to deal with very similar kind of ideas that we did in this video.